Okay, so here let's take a look at a sample problem about the Hall effect. So here it says a solid metal cube of edge length d equals 1.5 centimeter. So 1.5, 1.5, 1.5, moving in the positive y direction. So this cube is moving in the positive y direction. So here we have a red arrow pointing in the direction of positive y-axis. So with the velocity of a magnitude, this one, and then the cube move through a uniform magnetic field. So here we have a uniform magnetic field in the space, which is pointing to the positive z direction. Move to the positive z direction. So so here it asks for the question A is that which cube face is at a low electric potential and which is at higher electric potential because of the motion through the field. So it is slightly different from this case. This case is like you provide some potential, then there will be some current. And then if this wire is inside the magnetic field, then there will be some electromagnetic force, and then they're balancing, so that it will generate a Hall effect potential difference. So in this case, we don't provide any potential difference, but at the very beginning, so there will be no current, but we try to move this metal cube, so it is somehow like the electron is moving, because there should be some electron inside the metal cube, and then if you try to move this one, then it is somehow like the electron is moving upward, then there will be force acting on it. So of course you may ask, oh, there is some nuclear inside the metal cube, so why don't we count the positive charge? Because the positive nuclei are not free to move, so and even though the force acting on it, then the nuclei can't move, so we only count the free electrons. So here, suppose there are electrons inside it, and then we try to move this cube upward. So in that case, V cross B, so you use your finger point to the upper side, and then you cross to positive z-axis. So your thumb point to the right side. So here we have a V cross B points to the right side. And in that case, F should point to the left side, FB. The Lorentz force should point to the left side because it is a negative charge. So in that case, we should have this side is positive charge, and the other side, this side should be negative charge. So this is the answer to question A. So it asks you which is a lower electric potential, and actually we can actually measure the potential difference between the left face and right face to verify that. Okay, so the next question is, what is the potential difference between the phase of high and lower potential electric potential? So we can just make use of V equals small v times B times D. Okay, so as mentioned, V is 4 meters per second, so 4 times the B field is 0.05, and then the D is 1.5 centimeter, which is 0.015. So in that case, this should be 3 times 10 to minus third, or you can write it as volt, or you can write it as 3 millivolt. 3 millivolt. So actually, this potential difference is not large. It's not large. So you probably need some better equipment to really measure this potential difference. Okay, so next we talk about the circular motion, So a circular charged particle. So here it means that if we have the cross field, have the cross field, is it? Yeah, I think so. Here it says a beam of electron is projected into a chamber by a electric gun G. So here is G, although it is quite dark. So maybe I just change a color like this. So this is G, this is G, this is G. Okay, so the electron enter the plane of the page with a speed v. So it try to so it's go to the right side, but there are some it is not cross field. We only have magnetic field, isn't it? Yeah, we only have magnetic field pointing. Let's see, v cross b. So I think B field is pointing out of the page. The B field is pointing out of the page. Yeah, so the electron enter in the plane of the page with a speed v and then move in a region of the uniform magnetic field. Okay, so so the magnetic field B directed out of the plane. As a result, the magnetic force FB equals Q V cross B, which means that, for example, at this point, V is pointing to this side, and then B is pointing out of the page. So V cross B is pointing to that side. But this is a negative charge, so FB points to this way. And if the charge, so this charge will turn left. So for example, at this point, V is pointing this side, and then B is pointing out of the page. So V cross B point to the right side, and then FB point to the left side. So it turns out to be a circular motion like this. Yeah, which is so this is actually a circular motion. So even in high school physics, what you should know is that this is like ma, F equals ma. So F equals ma. So this is the concentral force. So the concentral force is actually the Lorentz force, or the or the magnetic force. So this is QVB, Q times V times B, and MA, A is actually V square over R. So even in high school physics, you should know this. Okay, so here we have a QVB equals M V square over R. We can actually cancel V and V on both sides, canceling V and this square. So it turns out to be QB equals MV over R. Or finally, we can just move this to the left side, move this side, move these terms over. So finally, we will have R on the left side, and then MV to here, and then QB on at the bottom. So this is the radius. This is the radius of the circular motion. So you can see M. So for a fixed particle, it should be a constant. And then V is a variable; it can change. And then Q is also a constant. Q is also a constant because it's an electron. So it is 1.6 times 10 to minus 19 coulomb. Okay, so there are two variables, V and B can be changed. So if we adjust this one, we can we can change the radius of the circular motion. So of course later on we will talk about the accelerator, 粒子加速器. So which means that we try to make the velocity of the particle as fast as possible, which means that we will try to make this one as large as possible. And in that case, we will also need to increase the radius of the circular motion, at least for the cyclotron. Okay, so yeah, so we will use this equation later. Okay, so here we have a sample problem. So here, an electron with a kinetic energy of 22.5 eV move into a region of a uniform magnetic field of magnitude, this number. So the angle between the direction of B and the electron velocity is 65.5 degrees. What is the pitch of the helical path taken by the electron? So here, the B field, we assume it pointing upward. And then the velocity, the initial velocity is pointing this side. Okay, so here, actually we can decompose the V in two directions. So one is this one is that one. So this is V parallel, which means that this V parallel is parallel with the vector B, the B field. And actually this V perpendicular is perpendicular to the B field. So we decompose this initial velocity into two components. Okay, so in that case, according to Lorentz force, so we know F equals Q V cross B. So here, V parallel, when we consider V parallel with a cross product, so which means that the angle between them is 0. So sine of 0 degree is 0. So this one doesn't contribute to the Lorentz force. Only the V perpendicular will contribute to the Lorentz force. So in this sense, in this direction, which means in this direction, just say this is Z direction, then the particle feel like a constant velocity movement, but in the xy plane, it will be something like the circular motion. So in that sense, when we try to add these two motions together, it will become a helix line. It will become a helix line, a 螺旋线. Because in this direction, it is a constant velocity movement, and then it also doing circular motion in the xy plane. Okay, so in that sense, it asks you the pitch of the helix path, which means that suppose we try to pick a point on the circular motion, and then we try to draw a line, parallel with the B. So it will connect with the next circular path. So this one is called a pitch. Maybe we can just call it P, which is the pitch of the helix line. Yeah, which means that if the pitch is larger, so this is something like this. If the pitch is smaller, it is something like this. So this is a small pitch, this is a large pitch. Okay, so it asks you how long is the pitch for the helix line. So first of all, we try to know the velocity first, because here we only know the kinetic energy. So as before, we use V equals square root of 2k over m. And then we try to plug in the numbers. K is 22.5 22.5 eV, and then multiply by 1.6 times 10 to minus 19. Okay, all over the mass of the electron is 9.11 times 10 to minus 31. Okay, so this velocity is 2.81 times 10 to the 6th power meter per second. Okay, so yeah, so next we try to calculate the pitch. The pitch will be V parallel times the period for the circular motion, which means that how much time it takes to go from, maybe I just change a color. So it starts from here and then it go this way, and then go to this point. So how long does it take to go for a circle? Yeah, but actually there are some z-axis movement, so it doesn't really go back to the original point. But yeah, so this is the time it takes from here to here, and then the movement in z direction. So we just multiply v parallel with the period, then it will be this movement, and actually this is the pitch of the helix line. So here we have a v times cosine of phi. V times cosine of phi. This is how we decompose it, the v in this direction. And then next is t. T is the length of the circle, which means that this is 2 pi r over v. V is v. This will be the period. And as in the previous page, we know r is mv over qb. R is mv over qb, so we have 2 pi over v, and then we have a mv over qb. So with some cancellation, v and v, then we will have it to be 2 pi m over qb. 2 pi m over qb is the period of the circular motion. So we have a 2 pi m over qb. Okay, so in that case, v is 2.81 times 10 to the 6th power, and then cosine of 65.5 degree. And then 2 pi is 2 pi, and then m is 9.11 times 10 to minus 31. And then Q is 1.6 times 10 to minus 19. And then times B is this one. B is this one. 4.55 times 10 to minus 4th power. Okay, so in that case, we can calculate that the pitch is 9.16 centimeter. Okay. Okay, any questions? Okay, so next we have another sample problem. So it says the essential of a mass spectrometer, which can be used to measure the mass of an ion of mass m to be measured, and charge Q is produced in the source S. So this one is the source. It generates the particle moving upwards, and then here is a slit, so it can enter the chamber. And then inside the chamber there is a magnetic field, the B field pointing out of the page. indicated by the green dots. Okay, so after entering the D field, it will go for a circular motion. But here is a screen, or we have a detector. So we detect which point the particle will drop into. So yeah, so it will block there. So rather than a whole circular motion, it only go for a half. Okay, so in that case, it says we'll charge the initial stationary ion is accelerated by the electric field due to the potential difference V. So from here to here, we have the potential difference by this battery. So it will accelerate the charge up to this point. And then the ion leaves S, enter a separate chamber in which a uniform magnetic field is perpendicular to the path. So a wider detector line at the line the bottom wall of the chamber. So this is the detector, and the cross of ion to move in a semicircle and thus strike the detector. Okay, suppose B, V, Q are these values. Strike the detector at a point that lie as X. So this is X, which is the diameter of the circular motion. Okay, what is the mass of the individual ion at the atomic mass? 1U equals this number. Okay, so here we will assume that there will be something like the conservation of energy inside this part, which means that the delta K plus delta U should be 0, for this part, which means that we have 1/2 of mv squared minus qv equals 0. Yeah, because here we have the battery, so there are some energy difference between this point and this point. So this energy should be Q times V, and then all this potential energy will transfer to the kinetic energy of the particle up to here. There will be no potential energy at all at this point. So all of the energy will change to the kinetic energy. So we will know the initial speed at this point. So in that case, we can have V equals 2qv over m, and then take the square root. So this is the initial velocity here. Okay, so next R equals mv over qb. This is the equation we just obtained in the previous page. So here we can plug in V equals this number to be here. So we have m over qb, and then V, change it to 2qv over m, and then take the square root of the whole term. Okay, so finally we can have some cancellation, which means that we can just multiply this m inside, become a m squared. Also, we can multiply q inside and then cancel with a q. So here we have 1 over b on from the outside, and then square root of 2 mv over q. So after making some cancellation. Okay, so in that case, x should be 2 times r. X is the diameter, so it should be 2 times of the radius. And it should be 2b times square root of 2mv over q. And then finally, what we want to find is the mass of the particle, which means that we would like to find m. So we just move all the terms over and then we try to find m. Or maybe we can first maybe we can also multiply all the things inside so that it makes things easier. So it becomes 8 mv over b squared q. So if we have a square root, so we just take square on both sides. Then we take square on both sides, we will have x squared, and then here we don't have the square root. Then finally, we can get m equals x squared b squared q over 8v, like this. Okay, so we can plug in all the values. X is this one. X is a 1.6254 square, and then times B is 80 millitesla, 80 times 10 to minus third power square, and then Q is this one times 1.6022 times 10 to minus 9, and then over 8 times 1000 volt. Okay, so finally this is 3.3863 times 10 to minus 25 kilogram. And then it asks you to represent the mass in this unit. So we just divide the answer by this value. We can get how many U. So this is actually 203.93 U. And this is the final answer. Which means that we just divide it by 1.6605 times 10 to minus 27 to get this. So with this number you can guess what should be this particle, how much proton or neutron it consists of. So it's around 204 unit, around 204 units, slightly less than 204. Okay, so here we try to talk about the cyclotron. So in Chinese it is called 回旋加速器. Okay. Yeah. So actually, for the particle accelerator, you may ask, why we need the particle accelerator? Actually, it is related to some development of the physics. So yeah. So in high school, you may have learned the periodic table. Yeah. So you know there are some so-called atom you cannot further separate into smaller one. If you really separate into smaller nuclear, then it becomes another element. And then actually in the high school chemistry, you also know that inside an atom there are something called proton, something called neutron, something called electron. And then the physician might ask, whether there are even smaller fundamental building block for this like electron, proton or neutron. For electron, the answer is no. You cannot further separate an electron into smaller particle, at least at this moment. But for proton and neutron, the answer is yes, you can further separate into smaller building block called the quarks. I suppose I have mentioned it before. If you have checked out just say, you can actually check out Yeah, actually check out 21, chapter 21. Yeah, as I mentioned here, we have even smaller particle, actually smaller building block for for the object in the universe. So it is called the standard model, 粒子的标准模型. So yeah, so as I mentioned, for the proton, you can separate into 2 up quarks and 1 down quarks, and for the neutron, you can separate into 1 up quark and 2 down quark. Then, yeah, if you try to add the charge, then it becomes a positive 1 for the proton and 0 for the neutron. And here you can also find electron here. Okay, so yeah, so far they know we have up quark and down quark, but whether we can find other things. So the physicians try to create the accelerator. They try to make the particle moving very fast, and then they collide with other particles to see whether after the collision there will be some new fundamental block comes out. So an analogy is like, just say, of course it's not very accurate, but yeah, just an analogy. So if you try to disassemble your smartphone, maybe some function is not good enough, or maybe just due to curiosity, you just try to disassemble a phone. So of course you can try to grab some tools to try to disassemble it, and then maybe you can just open the case, and then you try to see, there are some chips inside, and then maybe you need to use some other tools to disassemble it. And then another way to disassemble it, and it is much faster, is that you try to grab it and then you just flip it on the floor. you just throw it on the floor, and then your smartphone will just explode, and then there may be something coming out, which is much faster than using some tool to play with it. Yeah, so this is an analogy, but of course it's not so accurate. But yeah, the physician tried to do this, and as you can see here, so there are 3 generations of matter. So you can see this is the first generation, and you can see the mass. It is not represented by kilogram, rather than that is represented by MeV per c squared. So of course it is related to E equals mc squared. So equals relate to this one. So this is the energy of the particle, and then this is the speed of light. Of course this is a constant. And then so the mass is somehow related to the energy storing in the mass, and then divided by the speed of light squared. So here you can see for the first generation, so this is the energy, 2.2 mega eV, 4.7 mega eV. And then for the second generation, it's rated as 1.28 giga eV. So this is much larger than this one. And then for the third generation, it is even larger, 173 giga eV. Yeah, so yeah, more than 100 times larger. So maybe the physician may consider whether or not, if we can just accelerate the particle into a even larger, provide a larger energy, then maybe something like the 4th generation may come out. So this is why they would like to need the particle accelerator. Okay, so just go quite far away, just come back. So here, this is a fundamental cyclotron. Of course, it cannot accelerate the particle too much, so it is up to 50 mega eV, but the mechanism of the synchrotron is related to what we learned so far. So here we'll introduce it. So here is the synchrotron. It mentioned that the frequency. So we try to adjust the frequency, which means that here we have a disk. Our round disk. Okay, so all the particle will start from the center. And then here we have a disk, but we try to cut it in the middle. And then we try to separate it a bit. So we leave a gap in between. In that case, we try to generate a B field. We try to generate a B field in the disk. So there will be circular motion. But in this gap, we try to provide some potential difference so that it will try to accelerate in the middle. Accelerate in the middle, it will relate it to the radius. Just mention that R equals mv over qb, if you still remember. So here mb is of course a constant, and here b we cannot change in this case for the cyclotron. So the only variable is v and r. So we try to increase the velocity in the gap, and it will make the radius becomes larger. So you can see as it accelerates, the locus is something like this. It's something like this, and at the end, it will shoot out. Okay. So if you further need some more detail, I can just try to draw it here. So it means that suppose at the beginning, it tries to shoot out to the left side, and then there will be a velocity. So in that case, there will be a circular motion in this region. So it will go like this. And at this moment, we should change the potential difference. This side higher and this side lower. And in that case, it will generate an E field point to the right side, or maybe the other way around. Or it depends on whether or not it is a positive charge or negative charge. Suppose it is I'm not sure whether it is an electron or a proton. Let's see. I don't find it. So maybe we just assume it to be a proton, so it has a positive charge. So if the E field point to the right side in this region, only in this region, then it will accelerate. There will be A point to the right side, so the particle will accelerate. And in that case, suppose this is V0, this becomes V1 is larger than V0. So in that case, V becomes larger, R also becomes larger. So in that case, R going like this. So go to this point. And at this stage, we need to change the potential difference. This side higher, this side lower. Okay, so in that case, it will generate E field point to the left side. And in that case, the A will point to the left side. And it further accelerate. This is V1, and this become V2 is larger than V1. So it's going like this. So you just try to swap the polarity of the left side and right side back and forth. So if the frequency is accurate, then the particle will keep accelerating. So that's why we need to have this frequency to make the particle keeps accelerating. If it is not controlled properly, then when the particle is here, but you make the potential difference, this side is higher, then the A will point to the right side. Which decelerate the particle, so it's not good. So which means that given suppose we have Q, Q is fixed. We know the charge, and then 2 pi is a constant. M is also a constant. And then B is the magnetic is the B field magnitude we generate here. Actually, we cannot change it. We just make it a constant there. So actually this expression is the reciprocal of the period we just derived here. Here we derive this is the period of the circular motion. So taking the reciprocal of it, so F equals 1 over T will be QB over 2 pi M, like this. So which is actually this one. So we need to control the frequency of swapping the potential here. So that it keeps accelerate the particle. Okay. So a trade-off, a disadvantage of this one is that we need to generate the B field for the whole disk, which means that if we need, and as I mentioned, if we need a V to be larger, R also need to be larger, which means that if R is large, which means the area of it should be very large. So in that sense, we need to generate B field for a large area. So, but it consumes a lot of energy. As we learned before, the energy stored in the B field, I think we have not learned yet. But actually, for the energy stored in the B field, it is something like B squared over 2 mu, which is similar to energy stored in the E field, which is like a 1/2 epsilon naught E squared. So this is for the energy stored in the E field, and this is the energy stored in the B field. So you can see if we need B to be larger, we need more energy, and we need more energy in a larger area, which is a limitation. So we cannot accelerate the particle to a even higher energy for this setup. But at least this is its mechanism is easy to implement. So we just learn it here. Okay, so here we have another one called the synchrotron. The synchrotron is more complicated. We need to control the B field and the E field inside it, so that it is like a ring. So we try to control the B field and E field inside the ring, so that we try to make R to be a constant. As we know, R equals mv over qb. So M cannot move, Q cannot move. So here we try to fix R, so that we only need to generate a B field in a smaller region, and in that case we can make B larger. But actually we need to adjust B adequately. So the control is more complicated, but with this structure we can accelerate the particle up to 25 gigaeV. And of course we can have a proton synchrotron booster. So we try to pre-accelerate the particle up to 1.4 gigaeV, and then it followed by the proton synchrotron. Also, actually, we are accelerating proton, which puts the beam up to 25 gigaeV. So if you have interest, you can check it on the Wikipedia. Okay, so here we just talk about the particle accelerator, and if you have no question, let's stop here today.